Welcome to this explainer. Today we're jumping right into a really incredible journey. We are going to trace the entire evolutionary path of modern computing. We're going to start way down at the microscopic foundation, the absolute simplest building blocks of data, and then follow that exact same thread up through global networks, quantum security, and eventually right into the cutting-edge world of artificial intelligence. Honestly, it's a perfect masterclass in how human ingenuity builds massive complexity out of total simplicity.
To really wrap our heads around the digital world we live in, we have to start by asking a pretty fundamental question. How do simple binary switches, things that literally just flick on and off, eventually scale up to create machines that can basically learn to think? It sounds like magic, or a massive leap, right? But as you'll see, it's actually a highly logical progression of science and engineering.
Section 1. The Binary Foundation.
Okay, so to understand abstract data, we have to first look at the physical circuitry. We're talking about the actual hardware handling millions upon millions of electrical impulses every single second. Deep inside your phone or your laptop, there are microscopic switches. When one of these switches is turned on, an electrical current flows. When it's off, the current stops. That's it. That incredibly basic physical mechanism is the bedrock of absolutely everything a computer does.
The big takeaway here is that every piece of software you use, from a basic calculator app to a massive photorealistic video game, ultimately boils down to those two simple states, on or off. We represent this mathematically using the binary number system. It's a base 2 system using just the digits 0 and 1, which we call bits. And by stringing together enough of these bits and using specific mathematical rules to handle things like text or negative numbers, we can represent literally any piece of information in the universe.
But right away, we hit a bit of a roadblock. The real world isn't digital, is it? It's analog. It's continuous, it's messy, it's constantly changing. So knowing how those individual switches work, we have to ask, how do these computers actually step out of their rigid digital boxes and sense the physical environment around them?
Section 2. Capturing the real world.
To actually monitor our world, this hardware relies on a huge array of sensors. Think about the temperature sensors in your smart thermostat, or acoustic sensors listening for a breaking window. These are measuring continuous analog data, like the rising heat in a car engine or sound waves bouncing around a room. But remember, the computer only speaks binary, so all that real-world data has to pass through an analog to digital converter. This translates those physical properties into discrete digital signals, our ones and zeros. Only then can the computer actually analyze the data and react, like triggering an anti-lock braking system or setting off a burglar alarm.
Now, when we need to save all this sensory data, we rely on secondary storage. Hard disk drives, or HDDs, use magnetic platters that physically spin around 7,000 times a second. I mean, that is as fast as a sports car engine hitting the red line. But because they have moving parts, there's a slight delay. On the flip side, solid-state drives, or SSDs, use flash memory. They have zero moving parts. They rely purely on the movement of electrons, making them way faster and significantly more robust.
All right, so we've got devices that calculate in binary. They can sense the real world, and they can store massive amounts of data. But what happens when one isolated machine in, say, New York, needs to talk to another machine on the exact opposite side of the planet? How do we build that connected world?
Section 3. The Global Network.
Well, we start locally with local area networks, or LANs. This is basically the setup in your office or your home Wi-Fi. You might use a star topology where every single computer connects to a central switch. It's secure because that central switch directs data packets only to their specific intended destination. Or you might use a mesh network where nodes actively route data along the shortest possible path, sort of hopping from one device to the next. But of course, local networks are just the beginning.
Because the Earth is curved, we can't just use standard radio waves on the ground to connect these local networks globally. The signal would literally just shoot straight off into space. So we rely on vast satellite arrays. Low Earth orbit, or LEO satellites, hover a few hundred to a couple thousand kilometers up. They orbit extremely fast, which makes them perfect for mobile phone networks. Meanwhile, geostationary, or GEO satellites, sit way out there at 35,800 kilometers. They perfectly match the Earth's rotation, giving us constant, long-distance network communications across entire oceans.
But here's the scary part. With all our machines globally interconnected, beaming microwaves and radio waves right through the atmosphere, we've got a massive vulnerability. Theoretically, anyone could intercept those signals. Standard encryption is great, sure, but it can be broken. To actually solve this, computer science had to collide head-on with cutting-edge physics.
Section 4. The Quantum Security Leap.
By leveraging the physical properties of photons, which are particles of light, we move way past our simple binary bits and step into the wild world of qubits. Remember how a standard bit is either a 0 or a 1? Well, a qubit relies on quantum mechanics to exist as both 0 and 1 simultaneously. Think of a standard bit like a coin resting on the table, heads or tails. A qubit is like that coin actively spinning in the air. By changing the polarization of these photons, making them oscillate vertically, horizontally, or diagonally, we can encode incredibly complex data that's practically impossible to crack.
This mind-bending physical phenomenon is the foundation of the QKD protocol, or quantum key distribution. It's an absolutely ingenious step-by-step method used over fiber optic networks. The sender generates photons and pushes them through random polarizers. Down the line, the recipient uses random beam splitters to catch and read them, and then they compare notes. Now here is where it gets crazy. Because of the laws of quantum mechanics, if a hacker tries to intercept and read those photons mid-flight, the very act of observing them actually alters their quantum state. The sender and recipient instantly know the line is compromised. It creates an encryption key that is virtually unbreakable.
Okay, so we've scaled all the way up from a single circuit board to real-world sensors to a secure global network governed by quantum physics. Now we're at the ultimate frontier. What actually happens when these complex systems stop just following our instructions?
Section 5. The Age of AI. By building what we call artificial neural networks, we're essentially teaching machines to think in a way that mimics human cognition. We call this deep learning. Instead of giving a computer a strict, rigid set of rules to, say, identify a bird, we feed the network colossal data sets of unlabeled images. The neural network analyzes the binary codes of individual pixel densities. It looks for patterns, edges, and shapes, slowly building up a picture until it can independently recognize what it's looking at, even if it has never seen that specific image before. Believe it or not, this is exactly how your smartphone groups photos of your pets.
But you might be wondering, how does it actually learn from its mistakes? Well, it uses a brilliant mathematical process called backpropagation. The network takes a guess and then compares its output to the expected result. It calculates the error gradients, which is really just a fancy way of measuring exactly how wrong it was. Then it travels backwards through its own neural layers, slightly adjusting the weightings and the importance of each digital neuron. It repeats this process thousands, sometimes millions of times, until the errors are practically gone. This step-by-step process is literally the network training itself.
And there you have it. We have reached the destination of our journey today. We've moved from simple, microscopic on and off switches all the way to massive systems that learn without being explicitly programmed to do so. It's just a truly incredible evolution of hardware, networks, and algorithms, and it is undoubtedly going to define our future. So, I want to leave you with this one thought to chew on. If human ingenuity took us from basic binary switches to artificial brains in just a few short decades, what on earth will these networks teach themselves to do tomorrow?